So the last chapter, last unit we're going to look at before we start trade is on sequences and series. A sequence is basically a list of numbers, and then a series is when you add up a list of numbers. In both cases, kind of the goal is to find a pattern for the list. So like if we had a formula, and I ask you, what's the 5th term in the pattern? Well, that's pretty easy because it's not that far, right? But if I said, what's the 500th term? Well, depending on the pattern, it might be easier if we just had a formula that you could plug 500 into. Just plug in the number 500, do some arithmetic, and it tells you what the 500th term is. Right? So that's what we're going to start to try to figure out. Okay, so a sequence of numbers is a set of numbers that has a specific order to them. Okay, in other words, there has to be a pattern. If you can't find a pattern, you can't find a formula, we're not going to be able to work with the sequence. It's got to be something we can find a pattern for. Some patterns are very complicated. Okay, we're not going to get into any that are that complicated, especially if I'm asking you to figure out the formula. A couple basic patterns we look at is like adding the same number over and over to get from one term to the next, or multiplying by the same number to get from one term to the next. All right, so let's say we had a sequence, and I'm calling it sequence B. A lot of times the sequence is just named with a lowercase letter. It's like a variable. So sequence B. The first term in sequence B is written like that. It's a B with a small 1 next to it. A B with then the small 2 means the second term in sequence B. Then you've got the 3rd, the 4th, the 5th, the 6th, all the way up to what we usually call the nth term, however high it goes. Okay, there's 2 types of sequences. There's what we call an infinite sequence. That means it just keeps going forever. And then there's a finite. Finite means the sequence stops. So maybe you get to the 10th term, and that's it. It doesn't go past. Okay, so any question on that notation to describe the sequence position, term position? All right. And this one, you can kind of see what the pattern is. You're really just adding 1 to the denominator each time. So like the next term is 1/5, 1/6, 1/7. That one's a pretty kind of straightforward pattern. Okay, so now in order to have a sequence that is unique, there has to be a formula for finding the nth term. So if I was going to try to find a formula for that sequence up above, I would say it's this. That's the formula. If you want to know the 3rd term, do 1 over the number 3. If you want to know the 4th term, 1 over 4. The 600th term, 1 over 600. So it's a very, very simple formula, but you can just plug in a number, and it'll tell you what the term is at that number. Okay, so we're going to look at another sequence in a second, and I just want to see if we can come up with a formula for it.
Is that formula there? B in the end equals, yeah, that's what you're going to say. Thank you.
Yep, that's the formula for predicting the terms in that sequence up above. So if you want to know the 30th term, it would be 1 over 30. That's the pattern. Okay, let's look at the sequence. 2, 5, 8, 11, and so on. Okay, first of all, when you describe the terms in a sequence, the first number is in what we call the position 1. Okay, you start with position 1. So that's A1. That's the second term in sequence A, the third term, and so on. see if we can find a pattern for the nth term. Right? If we can find a pattern that predicts any term that we want to know. Okay, so what does it look like the pattern is here? A couple ways you can look at it, yeah?
They increase by 3.
Okay, so you take the one before the one you want to know, and you add 3. Okay, so this is the one we want to know. We're looking for the term in sequence A that's in the nth spot. What do you think is 1 before the nth spot? Yeah?
Just n minus 1.
Yep. So this represents the one before the one we want. And what do? You take the one before the one we want and do what?
Multiply by 3. Or no, add 3.
Add 3. Yeah, so that is a pattern that will work. So let's try it for like the 50th term. If you want to know the 50th term, what's the one that comes before it?
49.
So you need the 49th term, and what do you add to it?
Plus 3.
Plus 3. Okay, so now, do we know the 49th term?
Yeah.
Okay, then we need to find that. All right. So to get the 49th term, what's the one that comes before it?
48.
48th term. And what do we do to it?
Plus 3.
Plus 3. Okay, perfect. Do we know the 48th term?
No.
No. Then we got to keep going. We have to keep going until we finally get to a term that we know. So that kind of formula is okay, but the problem with it is to find the 50th term, you need to find every single one before it, not the most efficient way. Okay? This type of formula is called recursive. It works, but you have to find every single term before the one you want to know. Too much work. All right? Let's think of this a little bit different. So this is the first spot, second spot, third spot, and fourth spot. Instead of looking at the term that comes before it, look at the position of the term. Does somebody see something you can do with the number 4 to change it into 11? Or something you can do with the number 2 and change it into a 5? Yeah?
Would it be n minus 1 times 3 plus 2?
So you're saying do what with the number 2? Take the number 2.
So you take 1 away from it, you multiply that by 3, and you add 2.
Okay, it is a multiply by 3. There's a couple different ways you can look at it. You could also say just multiply this by 3 and subtract 1, which would be, I think it would come out to the same thing that you said. So another way to think of the pattern is look at the position number that you want to know, triple it, and then subtract 1. Let's try it. If we take 2 and triple it, what do you get?
6.
And then if you minus 1, perfect. If you take 4 and triple it,
12.
12, and then minus 1,
11.
11. Now, to get the 50th term, this is going to be very easy. Take the term position you want to know, 50, and triple it. What's 50? 150, and then minus 1.
149.
149. So now we know the 50th term is 149. And that's a lot easier than trying to think of it this way. They're both correct. This is better. Not as good. Okay. This is called the recursive formula with the red box. The green one is called an explicit formula. And I'll write those words down. Recursive is usually an easier formula to figure out, but it is not as useful. And if you're not sure how did we figure out to triple it and minus 1, I'm going to show you a way you can figure that out if you don't know how. Okay, so I told you there were 2 types of sequences. There are sequences that go on forever, and then there are ones that just stop. And infinite sequences are basically a sequence that goes on forever. So if we go back to this formula we had, a sub n equals 3n minus 1. if that represents an infinite sequence, which it does, the reason I know it does is right there. When you put dot, dot, dot on the end, it means it keeps going. That means you can plug any number you want in for n, as high as you want to go. Could you find the 1,000th term? Yep. 10,000? Sure. 10 million? Yep. You can just keep going. The domain for n is all positive integers. Now, it can't be negatives, because there's no such thing as like the negative third position in a sequence, or the negative fourth. The first spot in a sequence is position 1. Can't go below that. And how come n can't be a decimal if it's representing a position in a sequence?
Because it's describing how the set list of numbers go. It's like you can't have like the half set in sequence or whatever. You get what I'm saying?
Yeah, you can't be in between. It's almost like you're talking about people finishing a race. You know, there's
Right.
third place and there's fourth place. There's nobody who finishes between third and fourth. You don't get 3.4th place, 3.5th place. Right? So that's why when you have a formula for a sequence, the variable just represents positive integers. That's all you can plug in. And if it's an infinite sequence, go as high as you want. Now, if you compare that to a finite sequence, so a finite sequence would be a sequence that stops somewhere. So let's say that this sequence was 2, 5, 8, 11, 14. And that was it. That was the whole sequence. Then there's a limit to how high of a number you can fill in, because there's nothing after the number 14. It stops. What number would you plug in for n to get 14 in that formula? 5. First spot, second spot, third spot, fourth, and fifth. So the domain of this formula, in other words, the numbers you can fill in, are 1, 2, 3, 4, 5. That's it. Because it stops at 14. You'll know if it stops or not based on if you see a dot, dot, dot after the last number. Dot, dot, dot means it keeps going. Now, let's say n was 100 million. If you had 100 million terms in a sequence, is that infinite or is that finite? It's still finite. It's a lot, but it's still finite. It stops somewhere. Okay. So, any question on the difference between a sequence that goes on forever and a sequence that stops? Okay. So let's just practice listing out the first 3 terms and then the 15th term. And here's the formula. So it says the nth term is equal to n squared minus 1 divided by n. So all you have to do is plug in for n the term you want to know. Okay. What's the first one they want us to figure out? It's in what spot in the sequence? The first spot, yeah. N is 1. So you're going to fill in 1 for n. And then we do it up. What's 1 squared? 1. And then minus 1?
0.
So you end up with 0 divided by 1. 0. So the first number in this sequence is 0. Okay. What are we going to plug in to find the next number?
2.
2. So we're going to have 2 squared minus 2 divided by 2.
Just minus 1.
Yeah, minus 1. Thanks. What's 2 squared?
4.
And 4 minus 1? And there you go. There's the next term. 3 halves, or 1.5. Okay. What are we going to plug in to find the next one? Plug in 3. 3 squared minus 1 divided by 3. What's 3 squared minus 1? 8 divided by 3. Now let's do the 15th term. Okay. For that one, plug in 15 for n. Okay, what's 15 squared?
225.
225 minus 1 is 224 divided by 15. Now you might not notice it as a fraction, but these numbers are getting close to something else if you look at the problem. So we have 0. That doesn't really tell us much. What's 3 halves as a decimal?
1.5.
So that one's 1.5. Let's look at 8 divided by 3. 2.7. Okay, now let's look at 224 divided by 15. 14.93. What position is that number connected to?
2.
That's position 2. And this one?
3.
Position 3. And this one?
4. Oh, wait, sorry.
Yeah, position 15.
Yeah, that's it.
So what does it look like this number is getting closer to?
The position.
It's getting closer to the position number. It never quite gets to it. And the reason it never gets to it is because you're always messing the numerator up by 1. So it's never quite going to be the position number. But the further and further down you go, the closer this fraction is going to get to its position. 15 in that case. Yeah. Yeah, sign. Okay. Any question on plugging in a number and finding the terms?
Now, if you have this on a test, like you asked, like find the position number, and if you had something like this, would you find the answer that is closest to that position number?
So I'd be looking for what's in the green boxes. That's what I'd be looking for. Now, to find the 15th term, did we have to find the 14th term? Or the 13th or the 12th? No, we didn't have to find any of them because that's an explicit formula. If you want to find a term, you just fill in the number term you want. All right, let's try this one. So this is sequence B. And sequence B is -1 to the n times 2 to the n. Okay, let's start with the first one. -1 to the first times 2 to the first. Okay, Isaiah, what's -1 to the first power?
-1.
Yeah, -1. And what's 2 to the first power?
2.
2. And what does that give me?
-2.
Yep, -2. Okay, let's find the second term. So now fill in 2. So -1 squared and 2 to the second. Okay, Alex, what's -1 squared?
1.
Yep, it's going to be 1. And 2 to the second power? 4. And 1 times 4 gives me 4. Okay, once we do the third one, I think you'll start to see what the pattern is. So -1 cubed times 2 cubed. What's -1 cubed? It's going to be -1. And 2 cubed? 8. And -1 times 8? -8. What's happening each time?
It goes from a negative to a positive to a negative to a positive.
Yeah, first of all, this -1 to a power is causing it to alternate. So every other term is going to be positive, negative, and it's doubling at the same time. So the next one would be 16, and then
32.
And then negative 32, 64, negative 128. Yep. So which ones come out negative?
The one with the odd position.
Odd position ones are coming out negative. So when you do b to the 15th, is that going to be a positive or a negative?
Negative.
It's going to be a negative. And then all we have to do is really figure out this part. 2 to the 15th power. But we already know it's going to be a negative. So whatever 2 to the 15th is,
32,000.
768.
Yeah.
So that's negative 32, 768. If a number is in like the tens or the 100,000s, we'll write it out. If it starts to get in like the hundreds of billions, then we won't write it out. We would just leave it as like 2 to the 30th power. Okay, that'd be huge to write out. Okay, so any question on that one? So the formulas that I've been giving you so far to predict the next term, those are what we call explicit formulas. These are the best kind. An explicit formula allows you to find any term directly. You want to know the 3,406 term? Plug in 3,406 into the formula. So the other kind of formula that we can do is recursive. And that's one that you guys came up with for that first pattern. Okay, somebody said the pattern is take the one before and add 3. Okay, although a recursive formula is usually easier to figure out, it's not as useful. Okay, recursive formulas are kind of a pain. Because the other problem with them is if you mess up one time, you mess up everything. Because you're trying to find a number and you're always building it off the one you did before. So you mess up once, it's all messed up. So in a recursive formula, what I have to do is give you the first couple terms of a sequence. Say something like this. So I give you the first couple. And then I tell you something like a sub n equals the term before the one I want to know plus 2. That is the formula. Oh, I messed that up, didn't I? This would have to be an 8 to make the pattern work. And then I would have to fix this. That would be a 3. And that is the pattern for that one. It says take the term before and then add 3. Now, where do I say it? I say the first few. So I got to give you the first few. Why couldn't... If I just gave you one term like that, what would be the problem with me just giving you one term? Maybe. Or maybe, let's say I didn't even give you a term. What would be the problem with that?
You don't think what the pattern is.
You don't even know where to start. Okay, if I don't tell you the first term, well, this says take the term before the one you want to know and add 3. Well, if you don't have one to start with, you can't do that. So I've got to give you the first couple. And I have to give you a formula like that. So in a recursive formula, the first few terms are given. You'll get a formula that tells you what you're doing. And then you always use what came before to figure out the next one. Not a great type of formula. Okay. All right, but we'll try working with one. Right. So here's the first term in the sequence. And then what is this basically telling me to do right there? If you had to describe that to somebody that didn't understand like that notation, this is really just telling you to do what? Yep.
Add 3 to the term before.
Yeah, add 3 to the one that came before it. Yep. All right, let me scroll down a little bit. So based on that formula, what's the second term in the sequence? 5. Yeah, I think it's actually the one I just wrote down above. And then the third term would be 8. Yep. Now, if I said, what's the 900th term? Is that going to be quick?
Nope.
Not with that. You really need a better formula if you want to find the 900th term. Well, you got to figure out a trick to do it rather than just add 3, add 3, add 3, add 3, 900, or 897 more times. So any question on what a recursive formula looks like? So let's try this. So example 2, it says determine the first 4 terms and then the 8th term. And here's the information they give. So what are they giving you this time? Is that explicit or is that recursive? Yeah,
Recursive.
that's recursive. We don't like that one. Okay, so that's recursive. So determine the first 4 terms and the 8th term. Okay. So I got a chart. I'll write down the position and then the term in that position. Okay. What's the first term in the sequence?
2.
2. How do we know that?
It says it.
Yeah, it says it. That's a given. You can't calculate that. In a recursive, you got to be given the first one. Now we can go from here. What's the pattern?
Add 4 to the first.
Yeah.
Term 4.
Add 4 to the one that comes before the one you're looking for. Okay, so what's the second term?
6.
And the third term?
10.
And the fourth term?
14.
Now, even though we don't need 5, 6, and 7, the easiest way to get to 8 is to just do them. Okay, so what's the fifth term?
18.
18?
22. 26. 30.
And 30. So that's what they wanted, and that. So cursive isn't that bad if you only have to go up to like 7 or 8 terms. Even 10, 11, 12 terms, it's not that bad. But when you start getting into hundreds of thousands of terms, we're going to want to switch over to a better formula.
Are you gonna do something like on the test with a recursive formula? Like have us go that high or really high?
Maybe up to like 8 or 10. That would be the highest. Yeah, it wouldn't be something in like the thousands. Yeah. Okay. Any question on it? Okay. So now let's see if we can take something that is recursive and change it to explicit. In general, that's not easy for complicated formulas. Right? If I gave you a really complicated recursive formula, like let's say I did something like this. To get the nth term, you take triple, let's say something like triple the one that comes 2 before, and then take 5 times the one that comes right before it. Well, I messed that up a little bit. That would be a little complicated to figure out. So we're not going to do anything that complicated. So this says take triple the one that comes 2 before it, and then add 5 times what comes right before it. Probably not going to be easy to convert that to explicit. But since this only depends on the one that comes right before it, and you're doing something pretty simple, you're just adding 5, we can probably figure that out pretty easily. All right, so we got our first term. Let's do the first few. Let's even do up to the fourth term. Okay, what would the second term be? Second term would be 8. And the third term?
13.
So 13. And the fourth term? 18. Now, to convert it to explicit, the goal is to figure out something you can do to the number 1 and get an answer of 3. And then what can you do to 2 to get an answer of 8? And 3 to get an answer of 13. I'll give you a hint. It has something to do with a 5. Did anyone see what you can do with the position number to get the term? Yep.
Multiply by 5 and minus by 2.
Yep. It's times 5 minus 2. Let's try it. What's 3 times 5? 15 minus 2? There you go. Always check it with a couple and make sure it works. Because sometimes you find one that works for like the first one, but then it doesn't work for the second one. Like you might say, oh, I just take 1 and triple it. Triple 1, you get 3. Well, if you triple 2, you get 6. So that didn't work. Yeah, the pattern is times 5 minus 2. So now if you wanted the 100th term, that's easy. What's 5 times 100?
500.
And then minus 2.
498.
There you go. The 100th term is 498.
So for explicit formulas, we just you're just basically looking at like the base numbers.
Yes, for an explicit formula, you've got to figure out a calculation you can do with that number to get that number. You don't look at the one that came before it and say, okay, I'm going to add 5. Well, yeah, that's easy to see, but that's not a very useful pattern. Okay, so that was converting recursive to explicit. Any questions on that one? Okay. Right, let's try this one. So this is a special recursive sequence. You might have heard of it, maybe not. It's called a Fibonacci sequence. And the definition that's usually given for it is recursive. In the Fibonacci sequence, I have to start you off with the first 2 terms. The reason is because that's the formula for the Fibonacci sequence. What is that basically saying to do? To get a term, how do you do it? Yeah?
Take the one before plus take the one 2 times before.
Yeah. Take the one that's before it and add the one that came to before it. That's how you get the next term. Yep. That's why I have to start you off with the first 2. So what do you think the next term would be here if we add the 2 that came before it? Next one would be a 2. And then the next one would be a 3. And then 2 plus 3 is 5. And I don't know how many they want the first 6. Okay, that's it. Now that is not an easy formula to convert to explicit. It's not easy. So if I asked you what's the 900th Fibonacci number, well, you definitely don't want to keep doing it like this. It's going to take a while. But to convert it to explicit, it's not easy. It's very, very challenging.
So then you're not going to put it on the test.
Probably not that one. But there is a way to convert it. I don't remember how. But there is a formula that does it. And you can try it. Like this is the first one, the second one, the third one. It's not a simple thing like, times by 2 and then minus 5 or something. It's much more complicated than that. So any question on figuring out Fibonacci terms using a recursive formula? I might ask you to do something like that. But I don't have you go so high. All right. So I told you there are 2 special kinds of sequences we're going to look at. One is where you add a number over and over, and another one is where you multiply by a number. Now, first thing, how you pronounce that.
Arithmetic.
Some people say arithmetic. Some people say arithmetic. I say arithmetic. Yeah. And if you go on YouTube and you look it up, different people say it different ways. So some people call it an arithmetic sequence. I call it an arithmetic sequence. But when I do like 5 plus 2, I call that arithmetic. I don't. So it's the only time I've ever heard it pronounced that way is when you refer to it in terms of a sequence, an arithmetic sequence. But you can say it different ways. You can also call it a progression. Sequence and progression are the same. Same thing. All right. So let me show you an example first. Then I'll give you the definition. Let's say we had 13, 16, 19. I'll do one more.
Add 3.
Yeah, I want you to look at the difference. Okay, I want to look at the difference, which is kind of what you just said. But if you take 16 minus 13, what do you get? 3. And if you take 19 minus the one that came before it, what do you get? And 22 minus the one that came before it? 3. So the idea of an arithmetic sequence is if you take a term and you subtract the one that comes before it, if it always comes out the same, that's an arithmetic sequence. Okay. This is not an arithmetic sequence. It is a type of sequence, but that is not arithmetic. Because if you do 4 minus 2, what do you get?
2.
2. And what's 8 minus 4? 4, yeah, you get something different. So if you take something and subtract what comes before it, you need to get the same thing all of the time. And that thing that you get is called D. D stands for difference. So if you have an arithmetic sequence, D is what you call the common difference. It's the thing that you are adding each time to get from one term to the next. And the way you figure out what D is, take any term in the sequence and subtract the one immediately before it. That's how you find the common difference. And this kind of formula right here. What kind of formula is that? Is that explicit or is that recursive?
Recursive.
That's recursive. You're adding something to the previous term to get the next term. Well, I'm going to show you a way how you can automatically get an explicit formula if all you're doing is adding each time. And you're not going to have to try to guess, or is it 5n minus 2 or 3n plus 3? There's a thing you can do to figure out the pattern. And what we'll do is we'll go back. We did one that was like this. That one. I think it was, yeah, this one. Somehow somebody figured out the pattern here was 3n minus 1. Well, I'm going to show you how you can get that without guessing, okay, using a formula. So we'll come back to that. So this is going to be the explicit formula for an arithmetic sequence. Okay, it's going to depend on two things. If this was a sequence that I was trying to find a formula for, okay, just look at the one that's on the board. What do you think would be important to know about that sequence if you wanted to find a formula for it? Yeah?
That you adding 3 for each time you go to the next sequence. No?
Yep. So you need to know what are you adding each time. That's your common difference. And there's one other thing you would need to know. What you're adding each time and, yeah,
Your starting number.
where you start. Yeah. Those are the two things you need to know. So that's why in this formula, there are two things. A sub 1 is where do you start? and D is what you add each time. And remember this notation here, this means n is an integer. I think we talked about that really early on, that a capital Z is the symbol for an integer. And actually, I should even say positive integer. So when you come up with a formula for a sequence, you can't plug negatives into it because there's nothing before the first term. And you can't plug in decimals or fractions. So it's a sub 1 plus n minus 1 times d. So let's go back to one that we did and see if that works. Okay, just remember that. A sub 1 plus n minus 1 times d. Let's try. Where was it? I think it was on this page, maybe. Yep. Let's look at this. So somehow we figured out that it was 3n minus 1. 2, 5, 8, 11. What did it say the formula was? A sub... That formula we just wrote down?
A sub 1 plus n minus 1 times d.
Times d. Right. So what's the first term in this sequence? 2 plus, you don't fill in anything for n, you leave n. And what's the common difference? Like 5 minus 2, 8 minus 5, 3. Okay, that 3 is on the outside of parentheses. So what do you have to do with a number when it's outside parentheses? Multiply. Okay. Do I multiply it to the 2? No. What's 3 times n? 3n. What's
3
minus 3?
plus 2.
And now combine like terms. What's 2 minus 3?
Minus 1.
So 3n minus 1. Let's go back up and see if that's the same formula we got. Yeah, 3n minus 1. Okay, the difference is now you've got something you can plug into and you don't have to try to guess what the formula is. You just need to know the first term and what you add each time. And it'll automatically convert it to a formula for you. All right, let's try. I think I got another one of those. Okay, let's try this one. So this time, they didn't give me terms. I would figure out the first few terms and write them down. I usually do the first 4, so I can try to see the pattern. But you couldn't even do this problem the way it's written. Why not?
Because it doesn't give you a starting number.
I don't give you the starting numbers. I got to give you a starting number. And what do you want the starting term to be?
1.
1. 1?
100.
All right, we can do 1. 1. All right, so first term is 1. What would be the second term based on the formula? 4. And the third term? And we'll just do the fourth term. 10. Now, why don't we like that formula? It's recursive, right? We want to find the 200th term. We got to keep adding 3, adding 3, adding 3. It's going to take forever. So we want to try to convert this to explicit. Okay. What's the pattern that we use for an explicit formula?
Adding 3.
So I'm thinking, what's the formula?
3,
So it's got the n minus 1.
yeah, 3n minus 1.
Add 3 to
It's a sub 1 plus n minus 1
Times d. Yes.
Oh.
So this is going to give us a way to figure out the formula if you can't do it in your head. It gives you something you can plug into, and it gives you the answer. What's the first term? 1. First term is 1. And what are you adding each time to get from 1 to the next? 3. You're adding 3. Yep. So distribute the 3. What's n minus 1 times 3?
3n minus 3.
3n minus 3. Yep. And then when you combine like terms, what do you get?
3n minus 2.
3n minus 2. So if we did it right, that should be the formula. Triple the position and minus 2. Okay. Let's try it for 4. If you triple 4, you get
12.
and minus 2. Perfect. Triple 9. Triple 3.
9.
9. And then minus 2.
7.
7. Yep. So that's the formula. 3n minus 2. Okay. Any question on it? Alright. So let's try this one. The first 2 terms in an arithmetic sequence are -8 and -2. Let's see. So they want us to find, I'm going to reword this. So find a formula and then use it to get the 15th term. Now 15 is not that bad. I could figure out 15 just by doing the pattern for 13 more times. But if it was 150, we'd want to find the formula. All right, so let's write down what's the first term. -8. And what's the common difference? What do you do each time to get from one term to the next?
Add 6.
Add 6. Okay, so let's get our formula. It's the first term plus, what goes in parentheses there?
N minus 1.
N minus 1, and on the outside, the common difference, which in this case is 6. Okay, so when we do that, we're going to get -8 plus, what's n minus 1 times 6?
6 minus 6.
6n minus 6. And what's -8 minus 6?
-14.
-14. So that should be the pattern. Multiply by 6 and subtract 14. Okay. So now, let's find the 15th term. So to find the 15th term, what am I going to plug in for n?
15.
Plug in 15. Okay. What's 6 times 15? That's 90. And what's 90 minus 14?
76.
76. So any question on figuring out the formula and then getting this 15th term? Okay, so the key is you got to know the first term and you have to know what you're adding each time. Well, on this one, they didn't give you the first term. So how are we going to figure out, based on that table, what the first term is? What are we going to have to do?
Reverse engineer it.
Okay, so we know it's an arithmetic sequence. So what does that mean you have to be doing to get from one term to the next?
Adding a number to
Adding or subtracting. The same number every time. So we got to figure out, I would figure out how do you get from 13 to 3? What do you think you have to do each time?
Subtract something.
Minus 2.
You got to make 1, 2, 3, 4, 5 jumps, and you have to go down 10 units. How can you go down 10 units in 5 jumps?
Subtract 2.
Go down 2 each time. So we go 11, 9, 7, 5. So now we know the pattern. We can work backwards to get the first term. So what's the second term? in the first term? There you go. Now you got the first term. Okay, so first term is 17. And what's the common difference? Right, -2. You're going down 2. 5 minus 7. -2. Okay. Oops, space of that. So what comes right after the equal sign? 17 plus. That's always the same, n minus 1. And then times -2. Okay, so what are we distributing this time?
-2 and -1.
-2. Right. What does that give you when you distribute the -2?
-2n plus 2.
-2n plus 2. And the final answer.
-2n plus 19.
Yep. And let's try it on the let's try it and see if it works. Let's plug in 4. What's -2 times 4? -8. What's -8 plus 19? Think of it, 19 minus 8.
11.
Perfect. Yep. So that formula works. Any question on that? Here's another example of an arithmetic sequence. Right? And the last one we're going to look at is this type of sequence. All right. All right, how do you think you say that one?
Geometric.
I say geometric. No, I say geometric. So geometric. So I don't think there's any argument on that one, geometric. So in a geometric pattern, let me show you a geometric pattern and see if you can tell me the difference. That's a geometric pattern.
Multiplied by 2.
The key is you are multiplying each time.
So geometric is either multiplying or dividing, or just
Right. If it was dividing, you could see something like, let's say this was 120, 60, 30, 15. I would say the pattern there is you multiply by 1/2 each time. So you really have to figure out what you multiply by. Don't think of it as dividing. It's multiplying by 1/2 each time. Right? So the idea in this type of sequence is to get the next term, you multiply the previous term by a constant. Can't change what you multiply by. It's got to be the same thing all the way through. So how are we going to figure out what you multiply by each time if you were just looking at those examples? Well, what's 6 divided by 3?
2.
And 12 divided by 6?
2.
24 divided by 12?
2.
It's 2. If you take any term and divide by the one that came before it, that'll tell you what you're multiplying by each time. That's how you can figure it out. 30 divided by 60, 1/2. Now, when you take and divide two things, what do you call the answer? Well, I know you can call it a quotient. But anybody think of another word that has to do with fractions that begins with an R? Especially if you wrote something like this. Anyone remember how you read that in geometry? Ratio, right? 3 to 2, it's like a ratio. So that's why instead of using a D in this formula for common difference, we use R, where R is the common ratio. So the idea is to get R. I'm going to write it the way I just did with you guys. Take the term that comes after and divide by the one that comes right before it. That'll tell you R. So take 12, divide by the one that comes before it, 6. So this is fine as a recursive formula, but it's not that useful because if I said what's the 900th term in this sequence, I mean even if you put it in and use a calculator, it's still not going to be that great to figure it out. Right? 15 divided by 2 and divided by 2. So now you're at, I don't even know where I am. I'm at the 1, 2, 3, 4, 5. That's the sixth one. 7, 8, 9, 10, 11. I mean, you're going to do that till you get to 200. That's going to take a while. So we want to come up with an explicit formula that just gives it to us automatically. That is the explicit formula for a geometric sequence. Notice it depends on two things, just like the other one. You need to know where did you start and what did you multiply by each time. As long as you have those two things, it'll give you your formula. Let's try it on this one. Okay, in the pattern 3, 6, 12, 24, what's the first term?
3.
3. And what did I multiply by each time?
2.
2. Let's fill it in and see what happens. So to find a term, take the first term and multiply by 2 to the n minus 1. Okay, so here's the first one, second, third, fourth, and fifth. Let's try the third one. Plug in 3 for n. What's 3 minus 1? 2. What's 2 squared? 4. What's 4 times 3? 12. That's exactly what's in the third spot. So this is a pattern that would predict the nth term. If you plug in 4, 4 minus 1 is 3. 2 cubed is 8, and then 8 times 3, 24. I think some people have a harder time figuring this one out in their head, so now you don't need to. All you need to remember is this. And just fill in the first term, and fill in R. All right. Let's try, I think that's the last one. Okay, so let's find an explicit formula for that geometric sequence. Now, if I didn't write this down, you would have trouble doing this one. Because some people may look at this and say, okay, to get from -6 to 12, I'm going to say you add 18 each time. And that could be the pattern. But since I say geometric, you know you're not adding 18 to get to 12. What are you doing to get to 12?
Multiply by -2.
You're multiplying by -2. Geometric has to be multiplication. So this would be -24, yep. And I don't think we need them all. I think that's fine. Let's go work our way back. We do need the first one. What is it?
3.
First term is 3. And now we can find the formula. First term is 3. And what do you multiply by each time?
-2.
-2. Okay. What's the formula? You don't have to fill it in. Just tell me what the pattern is for a geometric sequence.
A1 times R to the n minus 1.
Okay. What's A1 here?
3.
3
-2.
times -2. You can't simplify that. Don't write -6. That doesn't work at all. Just leave it as 3 times -2 to the n minus 1. Let's see if it works to get the third term. What's 3 minus 1?
2.
2. What's -2 to the second power?
4.
4. And then times 3?
12.
Perfect. Yep. So that's the formula for finding a geometric sequence. Okay, so any questions on geometric or arithmetic sequence formulas? And I definitely, if you want to make a reference sheet, I would put those down so you have them. All right, that's the first section. So tomorrow and Wednesday, we'll do 11.2, split it into 2 days. All right, so that's the homework. So a lot of odds, it's all odds, except for 14. So 1 through 5 odd, 9 to 13 odd, 14, 17 to 27 odd, and 31. We will take a look at that first thing tomorrow.